All right, welcome back to your lecture for Friday, March 27th. Before we get started, I've received some complaints about the color palette and some of the colors not being able to be easily seen, so I have devised myself a more in the way but more color friendly, more viewer friendly set of colors. So take a look at all of these colors here and let me know on Piazza if any of those are difficult to make out or if you wouldn't be able to tell the difference between any of those. Hopefully with 12 colors available, I should be able to color code label everything. It is Friday, so quiz 9 does open today and is due Monday at 10 a.m. See Piazza for other announcements. Extensions keep happening almost daily, so I'm going to stop making announcements about when things are due on here, unless I'm pretty sure of the due date, and we are going to plan on getting back to regularly scheduled due dates as of Quiz 9. So Quiz 9 is due on Monday, and you are going to start having to use your late passes for these things. Starting with Quiz 9, unless you have contacted me about something specific to your situation. So, with all of that in mind, let's clear this off and get started with what we're going to do today. And that is inductance and inductors. And we just learned about magnetic induction last time with Faraday's law and Lenz's law. And magnetic induction is used in circuits. And when something that uses inductance and induction is used in circuits, it is called an inductor. So the actual circuit elements are called inductors. And they have a little symbol that is kind of a bunch of loops of wire. And that's really all an inductor is a bunch of loops of wire. And how good an inductor is at its job is called the inductance. To give a slightly more formal definition, inductance tells you how effectively that circuit element induces EMF in another device or another circuit element. And we'll talk about examples of when inductors will be used a little bit later, but for now I want to start off with defining the kind of two different kinds of inductance one at a time. One of these is called mutual inductance, which we're going to spend a little less time on mathematically, and the other one is self-inductance, which we're going to spend a little more time on. Oh, there's a red-winged blackbird at my bird feeder. Cool. So, with that in mind, I'm going to clear some space so that we can talk about mutual inductance. Mutual inductance is about how two circuit elements affect each other. So, to kind of get an idea of what's going on, let's consider two coils. Two coils of wire here and label them. One of them we will call coil 1, and coil 1 has N1 turns. So you get more bang for your buck in induction if you have multiple turns of wire making the same loop. So we're just going to call the number of times this wire goes around N1, and we're going to say there's a current flowing through this loop of I1. Then we're going to put this next to another coil of wire. We're going to call this one coil 2, and we're going to say it has N2 turns and a current flowing in it that is I2. So here's the basic idea of how this all works. I'm going to put my magnetic field in orange for this diagram. If there is a current flowing in coil 1, so we do have a current flowing, it's I1, then that means coil 1 is creating a magnetic field. And that magnetic field will make circles around the wire, and when you have a loop of wire, you end up with a magnetic field that kind of looks a lot like the dipole electric field. I'm doing my very best to make the perspective in this as obvious as I can, but I am not an artist and I am working with what tools I have available to me. It's kind of like saying I am not a lawyer, but it gets me out of having to draw things to scale. Now remember, all magnetic field lines eventually connect back around to each other. They don't just end off at infinity like electric field lines do. So all of these lines would loop back around and connect to themselves. I just don't have enough space to draw all of that. So this that I've drawn in orange is the magnetic field caused by coil 1. Well, now note, when we look at coil 2, we now have some of the magnetic field that was caused by coil 1 passing through this area right here. So we can say that coil 2 is now experiencing a magnetic flux. And this magnetic flux is caused by coil 1. And this flux that coil 2 experiences caused by coil 1, we're going to call phi sub 2, 1. Well, then the same thing also happens in reverse. So I'm going to draw the, let's see, trying to come up with good colors for this. We'll say, and we'll make it a different color. B2, because if there is current flowing around in coil 2, and I'll label that one in red. It could be either direction, but we'll call it I2. Make sure my current direction is consistent with. Okay, cool. Then coil 2 will also have its own magnetic field that it is creating. So pay special attention to which magnetic field is being created by and felt by which coil. And this is not the greatest diagram in the world. There's a lot going on here. So again, these magnetic field lines would loop back around and connect to each other. I'm just not drawing that. So current 2 in coil 2 causes magnetic field 2, the one in green. And this means that now I need a brand new color. What one haven't I used yet? Looks like yellow or pink. We'll go with pink. So now some of that magnetic field caused by coil 2 is passing through coil 1. So we can say that coil 1 experiences a magnetic flux caused by coil 2. And we are going to call this flux phi 1, 2. So the first number in the subscript of phi tells you which coil is experiencing the flux, and the second number tells you which coil is causing the flux. So hopefully you can see this situation, how these two circuit elements can affect each other. If we change the current through coil 1, if we change that blue I1, then we're changing the strength of that orange B1, the magnetic field caused by coil 1. Which means we're changing the flux that is passing through coil 2, which means we're going to induce a current in coil 2. And the same thing can happen in reverse. If we change I2, that changes the strength of magnetic field 2, which changes the flux that coil 1 is experiencing. So these two circuit elements can affect each other. A change in current in one will cause a change in current in the other one. And there's a mathematical quantity that defines this relationship called M, named the mutual inductance. And it is equal to N2 times phi 2, 1 divided by I1, or equivalently, N1 times phi 1, 2 divided by I2. So you can't have the mutual inductance of just a single coil of wire. You need two coils of wires, and the mutual inductance describes how those two coils relate to each other. The induced EMF, then in each of these coils, the induced EMF in coil 1 is negative m times the time derivative of the current in coil 2. Remember, it's I2 that's causing the EMF in coil 1. And vice versa, causing the EMF in coil 2 is the current in coil 1. And as always, if you just want an average EMF, you can replace the D's with deltas in these formulas. So, I want to talk about some examples of when we might actually see mutual inductance in a circuit or in real life. One of them that some of you may have, that I don't, is wireless charging devices. With wireless charging devices, you have to put your devices on some sort of special pad in order to charge them. Inside of the pad, there is a big loop of wire. And somewhere inside of your phone, there is also a big loop of wire, as big as possible to get the biggest amount of flux. So then, the wireless charging pad has some sort of changing current, usually an alternating current running through it. So if we consider the charging pad to be coil 1, we're changing I1, which changes the strength of B1, which changes the flux inside of the other device. So it changes the flux through the loop of wire in your cell phone, which generates a current in your cell phone, which is used to charge the battery. Another example of this is transformers. Not Optimus Prime, but those boxes near the tops of power poles. And transformers are used to change the voltage or the current, really both, you can't change one without changing the other, of some AC signal, alternating current. We haven't really talked about it in detail yet, but the current alternates the direction it travels very frequently. And a great example of this is power lines. Remember that real wires have resistance, so real wires do dissipate some voltage. And if you're a power company and you're trying to make money off of giving people power, you don't want to dissipate voltage. You want to keep as much of it as you can to deliver it to the consumer. So to do this, when you see the really beefy power transmission lines, you want to keep the current in those as low as possible. If the same amount of total energy is stored, then that means the power will remain the same. So if we want to drive the current down, we drive the voltage up. So we use something called a step up or step down transformer. When the power is going up into those big power lines, it's a step up transformer, which raises the voltage of the signal, which makes it more dangerous, and it's why they're further up off the ground, but lowers the current. So a lower current means less voltage dissipated because of resistance, and the power company conserves more power and saves money. So here, in this situation, you would want a high mutual inductance. There are other situations where you might want a low mutual inductance. One of those is the heating element in your washer or a washing machine. So here you might be wondering, well, what's the other device? So there's some sort of coil of wire in your washer that heats up in order to keep the water warm. But what's the other coil of wire here? And the answer is that the other coil of wire is the metal case of the washer itself. And we very specifically don't want to induce an EMF in the metal case of the washer. If we did, that would mean we could shock ourselves every time we touch the washer. So in this case, we want a small mutual inductance. So to address this, they do something called counterwinding, which you can see an example of in figure 14.3 in your book. But these are just some examples of how we actually use inductance in everyday circuits in real life. One thing to note is, coming back to our diagram here, coil 1 and the current in coil 1, I1, is creating magnetic field 1, B1, here in orange. Note that not all of my field lines for B1 actually pass through coil 2. So coil 2 is not getting as much magnetic flux as it possibly could, so we're actually wasting energy with this setup. Ideally, you want these coils to be practically on top of each other, so all of the magnetic field that goes through one also goes through the other. So that's all we're going to talk about in terms of mutual inductance. And now we're going to talk about something called self-inductance. So to talk about self-inductance, I want to have us imagine a circuit here. The circuit is a circular loop of wire that contains a battery and a resistor. The resistor is really only there so we don't get an infinite amount of current. It's not actually important to this process. Where this is a switch, and this is a battery, and this is a resistor. And we want to ask ourselves, if we close this switch, what happens? Well, if we close the switch, the first thing that happens is that current wants to flow, and current wants to flow in a direction that is counterclockwise. So once we close that switch, I'll draw that closed switch in blue. Current wants to flow clockwise. But this current is now going to create a magnetic flux. So I'll go to green next. So this current will create a magnetic flux through this loop. So if we use our second right-hand rule, we can see that the magnetic field B, and I'm going to call this the external flux, or magnetic field, is going to be into the page on the inside of the loop and out of the page on the outside of the loop. So now we're going to be creating an external flux into the page inside of this loop. Well, we just learned about this type of situation. So think we now have a loop of wire, and the flux through that loop of wire is changing. Think about what this should mean. So when you have the magnetic flux through a loop of wire and that loop or that flux is changing, you induce a flux. So the external flux through the loop just changed from 0 to into the board. So this means we are going to, the wire is going to, all on its own, induce a flux out of the board. So that means there's going to be an induced flux to oppose this change, so out of the board. So it's not just because the external flux is into the board, it's because the external flux is into the board and increasing. Reminder that it's the change in the external flux that is opposed, not the direction of the external flux. Well, think about what this last step that we just drew means for the current in the circuit. If we have an induced flux out of the board, Oh, you guys didn't correct my error. How dare you? That that original current I drew is actually flowing clockwise, not counterclockwise. I totally know how clocks work. So, if we have an induced flux out of the board, then that means we are going to induce a current to flow counterclockwise. So to label these currents a little more carefully, I'm going to call them external and induced. So that means that when we close this switch and current tries to start flowing clockwise, the process of induction, based on Faraday's law and Lenz's law, is going to fight against the external current. So the induced current fights against. And ultimately, what this means is that the current in the loop does not jump up instantly. Because the current in the loop, if we ignored magnetic induction effects, should be just the voltage of the battery divided by that resistance. But the induction happening in this loop means we won't reach that current right away. Inductors, much like induction in general, is all about fighting against changes. When we looked at Faraday's law last time, we saw any changes in the external flux were opposed by the induced flux and the induced current. Here, it's any changes in current and external current are opposed by the induced current. Just so you know, the inductor and the process of induction and Faraday's law will always eventually lose this battle. They will fight the good fight, opposing whatever changes they can, but eventually the external flux or the external current will win out. So, in words, this tendency of the circuit to oppose changes in current is called, wait for it, self-inductance. And self-inductance is given the variable L. So some formulas that can be useful here. There is the number of turns in the coil of whatever we're talking about. Most inductors have multiple turns to the coils, times the magnetic flux through that coil equals the inductance times the current flowing. Or the more important formula in my opinion, epsilon, the EMF of the inductor, so I'll put a subscript L there, or as I will more likely call it, V sub L, the voltage of the inductor, is negative the self-inductance times the rate in change of the current. And just a reminder, this is the external current we are talking about. So we can now kind of get an idea of what an inductor actually does. So if we have an inductor and we have current flowing through it in some particular direction, say the current is flowing through this way to the right, then what will this inductor do? So if this current is increasing, or trying to increase, the inductor will want to oppose this change, and it will induce current to the left. So if the current is increasing, this inductor will act like a battery facing against the direction of current flow. On the other hand, if that current, the red current I've labeled over there on the inductor, is decreasing, well, the inductor opposes all change in current. So if the current tries to decrease, the inductor sends reinforcement current, basically. So the inductor acts like a battery facing a direction consistent with current flow in the rest of the circuit. So the inductor just acts like a temporary battery in order to oppose whatever way the current is trying to change. And this is actually the goal of inductors in circuits. Inductors prevent circuits from changing current too rapidly. Sometimes circuit elements can be damaged if they go from 0 amps to 1 amps in the tiniest fraction of a second. Sometimes you need to slowly ramp up that current in order to avoid damaging the electronics themselves. And this is what inductors do. They can prevent the current from rising too rapidly and damaging circuit components. Also, if there are intermittent power failures, brief ones, say the power cuts off for a millisecond every minute or so, the inductor can stop the current from dropping to 0 and allow the circuit to continue running at least for a little amount of time, an amount of time that will be defined by a time constant when we do the example we're doing after this. This is also the reason why when you're told to restart things like your router, they tell you to unplug it and leave it unplugged or leave it off for 10 seconds before you plug it back in. Well, that might seem stupid if you think, well, electricity travels at the speed of light, so shouldn't it all turn off pretty much instantly? And the answer is, well, kind of. There are actually inductors in those circuits. So when you unplug your router or your modem from the wall, some current still flows being powered by the inductors, acting like batteries because the current is trying to change from whatever it was to 0, and the inductors fight that change. They keep sending current along those same paths, at least for a little while before they give up the ghost and the whole circuit dies. So that's the reason you actually need to leave some things off for 10 seconds before restarting them for it to be effective. The last thing we're going to talk about is the RL circuit, which we won't have a ton of time to talk about, but at least will give us an idea how inductors work in terms of equations. So we have a battery and a similar circuit to what we had before with a switch that can go one of two places. And with an RL circuit, we have a resistor and an inductor. And we're going to consider this switch in two locations. One of them is if we connect the switch here in red, and the other one is if we connect the switch here in blue, and I'm going to draw what happens in these situations separately. Oh, if you guys will forgive me, I have these colors opposite in my notes, and I don't want to confuse myself. So 1 will be in red, or 1 will be in blue, and 2 will be in red. There we go. So if we connect the switch to 1, the current is going to try to rise from 0 to, well, the current eventually wants to be at a value consistent with Ohm's law. So if we have the entire battery voltage spent at the resistor, we'll call this I max. The current is going to try to rise from 0 to I max, but the inductor is going to fight this change. So when we actually connect the circuit like this, current, what I've been calling the external current, is going to try to flow this way around the circuit. Well, what an inductor does is opposes the change in current. Current is trying to go from 0 through the inductor to down through the inductor. So this means our inductor is going to act like a battery pointed against the direction of current flow with a voltage of V sub L or epsilon of L. I'm going to kind of use the two interchangeably. The inductor will eventually not win this change, or win this fight, but it will fight it for a while and prevent the current from rising instantaneously. So what we end up with here is, in terms of you have to spend all of the voltage that you get from the battery, well, we get voltage from the battery, and we will lose voltage at the resistor, and we will lose voltage at the inductor. So imagine doing a Kirchhoff loop through here. We add the battery voltage because the loop goes forward through the battery. We subtract the resistor voltage because we're following the current through the resistor. And then think of this inductor like a battery. We're going through this battery backwards, so we would subtract the battery voltage and then subtract the inductor voltage. Set it all equal to 0, or rearranging, we get this. So, well, the voltage across a resistor is just IR, and the voltage through an inductor is L di dt. You'll note that I've dropped the negative sign there because I've already accounted for whether I'm adding or subtracting these voltages, so all I need is the magnitude right now. And this gives us a differential equation that you do not need to be able to solve, but this is the equation that you would solve to get the following equations. And I'm just going to do these all in cool colors. So purples, blues, and greens. I'll go with situation 1. So the current in the circuit will be equal to VB over R, or Imax, times 1 minus e to the negative t over tau. And the voltage across the resistor will be the current through the circuit times the resistance. So this will just be the battery voltage times 1 minus e to the negative t over our time constant tau, which I'll talk about in just a little second. And then we could find the voltage across the inductor by literally taking a derivative of the formula for the current in the circuit. So voltage across the inductor is then the voltage across the battery times e to the negative t over tau. So when we're in situation 1, these are the equations that we have. And I want to draw a graph to kind of show what's going on here. So if we put a graph up here, and we label the battery voltage over time, we're going to have a couple of different things happening here. One of them is that our resistor voltage starts off at 0 and rises asymptotically up to VB. So this is VR. And then our inductor voltage will do the opposite. It'll start up at VB and asymptotically drop down to 0. So to begin with, the inductor has all of the voltage, and eventually at the end of the day, the resistor has all of the voltage. So I need to clear a little bit of space here. And we'll get back to that. So hopefully that'll be okay. Should be able to make do with that. So now that time constant tau. For a RC circuit, it was equal to R times C. For an inductance circuit, an RL circuit, it's equal to L over R. And as to why you should expect these values, if you have a large inductance, that means the inductor is better at fighting the change in current. So the current takes longer to change. So a bigger inductance means a harder fight back against the change in current. So that change takes longer. On the flip side here, a small r means a bigger change in current. Because remember, V equals IR, so the maximum current down here, if we pick a smaller r, we get a larger maximum current. So we get a larger change in current, which means the inductor fights back harder. And that is our time constant for this circuit. Real quickly, I want to talk about what happens when we then connect our switch to 2. So now, current is going to, not tires, current tries to drop from whatever its initial value is, say I max, to 0. So the current was initially flowing at I external, and it's going to try to decrease down to 0. Well, when the current through an inductor is decreasing, that inductor acts like a battery oriented the same direction as the current. Again, these are both for the inductor right there. Still has a voltage of V sub L or epsilon sub L, but in the absence of an actual battery in this circuit, the inductor will act like our battery. So we have the relationship that all the voltage you get from the battery, which is the inductor voltage in this case, equals the voltage you spend at the resistor. So we get a couple of pretty straightforward equations here. Again, everything drops. So the current in this circuit is whatever the maximum current was. Let's say we let this thing charge all the way up to the maximum current, times e to the negative t over tau, same tau as before. And then the voltage across our resistor and the voltage across our inductor, at least in terms of magnitudes, are just the initial voltage, or assuming the battery voltage, times e to the negative t over tau. And these are the equations that we will need. So, kind of making another little graph right here, where this is our original voltage, VB. Now we have the inductor voltage dropping exponentially over time. And we also have, nope, not that color. I'll go with yellow. And we also have the resistor voltage dropping at the same rate. Briefly, at least, I want to compare and contrast the RC circuit with the RL circuit. One difference is the time constant. The time constant equals RC in an RC circuit. It equals R over L in the RL circuit. Another thing I want to look at is what happens initially. So initially, right when you close the switch in an RC circuit, the current does flow, and the resistor voltage is taking up all the battery voltage while the capacitor voltage is 0 because no charge is stored yet. In an RL circuit, when you connect it, the current does not flow at first. And all of the battery voltage is spent at the inductor instead, and the voltage across the resistor is 0. And then at the end of the day, in an RC circuit, the current flowed until the capacitor became fully charged. And once the capacitor is fully charged, then no more current flows. And the voltage on the capacitor is now equal to the battery voltage, and the voltage across the resistor is 0. Conversely, for the RL circuit, after a long amount of time, after some amount of time, the current does flow. And all of our battery voltage is being spent at the resistor, and our inductor has 0 volts on it. So these are two kind of complementary types of circuits, at least for DC circuits. An RC circuit acts like just a resistor to begin with. Current immediately starts flowing as though the resistor were the only thing there were, but after a long amount of time, an RC circuit acts like a break in the circuit and current does not flow. For the RL circuit, on the other hand, initially it acts like a break in the circuit, and current doesn't start right away or doesn't rise as steeply as it would. But after a certain amount of time, then the circuit acts like the inductor isn't even there and current flows freely. That's all the time we have for today. Make sure you check Piazza for announcements and let me know what you think of the new colors. That's everything, and have a good day.